Okay, let's come back to the slides. As you remember, I already explained the so-called wave disturbance for liquid jet to be a breakup into small droplets. Where I introduced this concept before, and here I mentioned there is the balance between the surface tension and the aerodynamic resistance. The competition between the surface tension and the aerodynamic resistance will give you the different kinds of breakup process for a liquid jet. But the initial the nucleation of these kinds of instability basically coming from the so-called wave disturbance. Okay, mainly I mentioned by the blue lettering. They tell you there is the three effects governing all the breakup mechanism of a liquid jet. Usually, we call this kinds of breakup of the liquid jet is the so-called instability of a capillary jet. Okay, and I already mentioned those wave disturbance maybe come from the surface disturbance by the outer fluctuation in the surrounding, or maybe you can have some pressure disturbance or velocity disturbance, even the temperature disturbance based on the property change of the liquid. Those kinds of disturbance give you some wave motions on the liquid jet. And this wave motion will be governed by the balance between the surface tension and aerodynamic resistance, and result in different kinds of breakup process. Okay, and I give you the example for the figure one case. They tell you those kinds of disturbance is not fit with the frequency were determined by radar predictions. Then you will have an irregular droplet distribution occurs for a jet breakup. And if you have a shorter, smaller disturbance for this case, the wavelength, the wavelength to the diameters is around 4.6, is more than the previous one, 11.3. Then you will produce the very nice droplets breakups, and you can have a spherical droplet at the end of the breakup, the breakup droplets. Okay, and those kinds of the suitable wavelengths for the breakups will be determined by radar predictions. Later on, I will introduce it. Okay. Now let's look at the experimental observation. Here you can see I mentioned those kinds of inference coming from the aerodynamic resistance and also the surface tension, and we will find out those interactions will be observed from the experimental observation here for a single jet, very tiny liquid jet coming out. And here there is I change the total volume flow rate of liquid from the zero point 0.2 up to 0.5. That means that we increase the exit velocity of the liquid jet from left hand side to the right hand side. Okay, and the loss structure actually can be described by the figures shown in the right figures. Actually, it's not totally fit, but they just give you the idea for the initial breakup process and governed by radar theory. Okay, let's look at these figures that tell you if you increase the velocity, then you will find out that the breakup length. A definition of breakup length means that you starting from look at the exit plane of your liquid jet, and to find out where is the separation of your liquid jet to the droplet, and you determine this is from this point to the exit plane of your jet. Then we call this as a so-called breakup length. Okay. Now you can see if you increase the injection velocity, actually the breakup length is initially increased very linearly to the highest point. Okay, but when you increase the injection velocity further, those kinds of breakup lengths will be reduced, and you can see the different structure when induced. When induced, because now the air resistance become too strong, those kinds of wave coming from the shear force acting on the surface becomes stronger, not governed by the capillary effect. The first part, the B region, basically controlled by the instability of radii, described by the radii instability, and basically those controlled by the, as I mentioned here, is about capillary jet influence. Okay, then you can see there is the linearly increase in breakup length. But when you go to the region C, the main controlling factor basically coming from the aerodynamic resistance, then they will drop to the minima. Later on, they will go to the second induced wind influence. Okay, and this will be another mechanism. I do not have too much time to describe it. But later on, you can see when you go to the E, they will go to the so-called atomization mechanism here, as I mentioned from our previous discussion from our lecture notes. Okay, this is the several regions from B to C to D to E by changing your injection velocity. But now, from the experiment observation shown in the left-hand side, basically we just described the region B belong to the radii theory. Okay, you can see by increasing the flow rate, you can see there is the extension of your breakup length, right? There is a very small breakup length for the 0.2 uh, 0.2 milliliter per second, and Q 0.3, then you can see breakup length increase, and the increase 2 for the 0.4, and 4.5, they almost increase not too much. But those kinds of extension of the breakup length actually fit well with this line. But when you look at the breakup structures, and maybe we go to the next slides here. Okay, you can see they can produce the droplets, but sometimes they have some satellites. This is the naturally flow out the liquid jet. But when you try to control a very nice periodically occur spherical droplet, you can try the some excitation on it to maintain those kinds of wave disturbance fit well with the fixed frequency. If you try to use the forcing, as I described earlier, you use the piezoelectric forcing on the liquid jet, and this kinds of forcing is governed by the fixed frequency, then those kinds of fixed frequency will give you a suitable wavelength to break up the droplet as the very constant separation distance and width, and also has the constant droplet size generate. Okay, this is a two different structure I want to show you. The left-hand side, basically, they just give you an idea. There is the nature flowing out liquid jet, and there has a breakup point at the very far downstreams of the liquid jet. But when you're forcing a certain frequency, in this case is 4,000 hertz, and by this condition you can produce the periodical occurring droplets with the constant uniform droplet size and a constant separation distance, because these kinds of excitation fit very well with the wave length required for breakup. Okay, this is a system we used for our previous free-falling droplet experiment system. Okay, now we just give you the idea about a single smaller liquid jet. But if you increase the diameter of a liquid jet, that means that you try to apply more liquids into a combustion chamber, then you need to think about additionally on the large amount of liquid effect. Okay, for example, this is a cross sections of a large diameter of a liquid jet, which means that when you have a liquid flowing in the inner jet of of the injectors, actually they just like a pipe flow. They may not have a so-called uniform velocity profile, which means if you take a different kinds of cross sections, if you have a cross section with different region, for example, for the region 1, actually the flow in the region 1 has a higher velocity, right? And you can see this is some kinds of velocity distribution, or you just look at liquid surface front, the front surface. You can see that for the region 1, liquid has a higher velocity. They can move, has a higher actual momentum, and then they will move ahead. And for the region 2, they have a smaller velocity. They were a little bit behind of the inner jet. Okay. And for the region, the fluid in the region 4, very close to the surface of the injectors, they will experience the shear force on the wall surface. Then they have a lower velocity, which means that they were far behind of the liquid front in the region 1. In this sense, they have its own velocity difference for different regions. Then you will see the first one, when all the liquids impinge out just at the surface, at the exit plane of the surface, you will find out they were spreading into a so-called a cone. And this cone basically they contains several layers, okay, because they have a different velocity. For example, flow velocity at region 4 is smaller than that in the region 3, then they will have some kinds of shear force between these two regions. Okay, and in this sense, they will find out the first one, they will try, because all the inertia coming out along the actual directions, but they will expand to the radial directions. Then the liquid coming out will as a spread cone. And in this case, the air will come in from the outer surrounding entrance into the spread cone. The entrainment of air and the division of fuel spray. There is the division of fuel spray for this example is separate as the 4 region, right? Then the division of fuel, because there velocity difference between regions, right? Okay, these two effects will make the spray into a concentric conical spray. Concentric, there is the several cone, right? There's the outer cone, and then the center cone around here, and this cone is produced by region 2, and this cone is produced by region 3. Okay, and by this kinds of structures, you may have air entrainment into the interior region between different spray cone. And those kinds of, for individual spray cone, you will find there is some wave occurs on the liquid sheet surface. Okay. And those kinds of wave disturbance, just like a wave disturbance on a small liquid jet, they will have increased intensity to break up the liquid sheet to the ligament. Okay, here you can see this is a cross section of one of liquid ligament. Ligament means just like a donut. Okay, this is a donut, but you take a cross section, then you just can see the cross section of the donut. Okay. And those kinds of wave disturbance will continuous occurs on the ligament, and to make the ligament break up into the droplets. Okay, and finally, if you go to the downstreams, those droplets may have an interaction between droplets. Then they have some agglomeration or separation to small droplet or become a larger droplets. Okay. This is a typical mechanism for a liquid current. Liquid current is different from the previous small liquid jet. Liquid current means they have a large cross sections. That means the liquid velocity on a given cross section of a liquid jet were different. Those velocity difference will tear your spread, your liquid as a different layer. When they're coming out of the exit plane of the jet, they will tear to the different layer of a spread of a liquid spread. Okay, and those kinds of wave disturbance start first acting on the liquid sheet and try to break up the liquid sheet to ligament. And those wave disturbance on the liquid ligament later on they break up the ligament into the liquid droplets. I will give you the detailed description is like this. For example, here the impinging out, the spray coming out. Okay, here you can see initially you will have a spray surface. We call this as a liquid sheet. Okay, liquid sheet is a liquid sheet, something like that. It's a sheet. And when they're coming out, the wavelength, the wave disturbance will occur on the liquid sheet, something like this. Then you can see the growth of wave on the sheet. Okay, when the intensity of the wave disturbance is large enough, they will break up the sheet into the ligament. Okay, this is the ligament. In the case for the spray cone, actual ligament is just like a donut. Okay, and you can you can figure out there is the wave disturbance on the sheet, and those wave disturbance also will occur on the ligament. Okay, you can see this ligament has a certain wavelength occur on that, and this wavelength will further break up the ligament into the droplets. Okay, now you can see the breakup process for a current of liquid. That means the large volume of the liquid is look like this. They will starting from the liquid sheet and to the ligament and finally to the liquid droplets. I give you the typical experiment result, and this is coming from the a spray nozzle. Actually, you can see near the tip of the nozzle there is a region. Actually, they show you as a spray cone. Basically, they have a surface, liquid surface. Then you can see there is some disturbance occurs on the liquid surface, and this disturbance will break up the sheet into the ligament. You can see there is some ligament occur here, and those ligaments will be further break up to the droplets. Finally, in this region, they will show you a lot of tiny droplets distributed in different locations. Yeah, I give you a very interesting experiment. Actually, you can do this kinds of experiment by yourself, and I hope you can do it by in your dorm. And how to do it? Actually, I did this experiment by asking students to do it because I have this kinds of observation from the kitchen. At that time, I was asked to wash the bowl after the dinner by my wife, and I need to help to wash the dishes. And at that time, when I bring the bowl for washing, and I use water, and I find out surprisingly when you turn on the water and impinge on the curved surface of the bowl, and I just find out there is some breakup mechanism nicely presented. And at that moment, I think we may have some good experiments. Ask the students to have some observation. And this is a very simple and a typical example for the liquid sheet breakup. You can use it for the experiment to show here. We use the cylinder of this is just actually this is the burner. The burner we use for the upholstery floor. Okay, and this is just a pipe, and we just let the water coming out and to impinge on the curved surface. Actually, you can see this is a front view, and this picture is from the side view. You already see there is the distribution on the liquid jet. Okay, coming from the floater. Okay, you can see already there is some wave disturbance. But anyway, when water impinges on the curved surface, they initially produce the liquid surface. Okay, you can see liquid surface. And on the liquid surface, you can see there is some wave occurrence. There is a wave. Okay, and this wave disturbance was strong enough to break the liquid surface into the liquid ligament. Okay, this is water ligament. And you further you can find out those kinds of water ligament will be separated to a tiny droplet. Yeah, this is a very nice experiment to show you the detailed breakup mechanism for from the liquid sheet to the ligament and to the droplets. If you can try, I think this will be your assignment, and please go back, go home, go to your dorm, try to do the experiment, try to use the different kinds of curved surface, and you try to experience those kinds of breakup mechanism. I think you can take the picture easily without using a high-speed camera. You can use your cell phone and take a picture as the evidence for your experimental observation in this week. This will be the your assignment. Okay. Okay, now we go to the more real application for industry side. I give you the example for the simplex atomizer, as I mentioned before. The mechanism for simplex atomizer here, this is a typical mechanism I want to explain. They tell you the liquid fuel coming from the tangential directions, then they flow into the chamber or inside of the injector, then they will produce the circulation, the swirling. Those kinds of swirling motion will push your liquid coming out, okay? And when they're coming out, those kinds of swirling motion will give you the centrifugal force to push your liquid to expand their spray cone radially outward. Okay, and this we call this a simplex nozzle. For a given simplex nozzle, you will find out they will show you different kinds of mechanism, spray atomizing mechanism by increasing the velocity. In this case, actually, increase velocity relate to the increase in the supply pressure. Okay. For the lower velocity, actually, you do not have a so-called atomizing mechanism. Actually, they just a small, tiny liquid jet coming out. Now, you increase your flow velocities, then that means the swirling motion increased, and also the pressure will push the liquid out, then spray angle will be open, and like this. But in this case, since the velocity is too low, the strong atomization, the wave disturbance is not too strong. That means the liquid sheet can extend to a longer distance. Then you can see these are some kinds of so-called onion shape. I think you look at the onion is a several layer, right? And those kinds of surface look like a full surface. This is a full surface, and they have some wave disturbance as I showed before. Here there is some wave disturbance on the liquid surface, liquid sheet. Okay. But later on, you can see there is some atomization occurs at the end of the liquid sheet. Now, okay, and sometimes they will have some bubble or broken area occurs on the liquid surface, and in the downstream of the spray, they have some ligaments, and also the droplets occurs. Okay. Now you increase the velocity further, you can see the pictures move to the so-called tulip tulip shape spray cone. Tulip, there is a smaller liquid sheet area, okay, but here they have a very many ligaments occurs, and finally you can see the droplet size, many droplets occurs in the downstream. Higher, if you even go to the very high velocity, you can see by increasing the velocity from small to the high, actually initially they produce a liquid sheet region will be reduced smaller. For example, for the onion shape, they have a large liquid sheet, right? But for the tulip, they will shrink to a small area as a liquid sheet. But for the very high velocity, actually you cannot see the sheet. Even you do not have a very detectable ligament occur. They just have a very fine droplet occurs very close to the tip of the injector. Okay. Now in this case, actually this is a fully atomizing spray you may have. Okay. Therefore, you can find out the mechanism from the very almost no atomization to fully atomization, basically by controlled by your flow velocity. Actually, this is represents the influence coming from the aerodynamic resistance is increased stronger, and stronger. Okay, then they will they will enlarge the wavelengths on the liquid sheet and to the ligament and to produce the tiny droplets. This is the mechanism for the simplex atomizers. I did this kinds of experiment by using the different kinds of experiment. Here, we try to duplicate the mechanism of the simplex nozzle. We use the two, I forgot to the English, lodo, two lodo together. I cut the small tube and I put the two lodo together, and I try to introduce the water tangentially into these mechanisms, and I try to increase the flow rate. You can see the flow rate starting from the 53.7 milliliter per second and increase up to the 200. You can see initially they do not have an opening of the spray. Gradually, the spray nozzle increase, and you can see the liquid surface, liquid sheet occurs and enlarge, and there is some kinds of hole occur on the surface. Okay, and finally, you can see there is some breakup ligament and droplets, and this can be observed by a serious experiment. And we take examples from here, and you can see those kind. Actually, we use this idea to duplicate the simplex nozzle. This is a duplicate simplex nozzle to tell you the atomization mechanisms. And I shine a laser to see the cross section. Actually, I try to measure the cone angle. Okay, this is a typical experiment from the duplicate simplex nozzle. Okay, let's look. Go back to the let me show you another example. We already explained from the slides in our lecture notes. We already explained those kinds of breakup mechanism from the sheet to the ligament and also to the droplets. Okay, I just give you the final examples. Okay, for the trim fluid. Okay, the trim fluid basically you can see these structures described by Muller and Chigel in 1974 for the internal mixing trim fluid atomizer, and shown in the page 3.7. You can see the liquid fuel coming from the this night and the air flowing from the center night. They will mix together here. Then we call this as an intermixtion. Okay. For the intermixtion, because liquid fuel easier to attach to the liquid to the surface, and you can see the interaction starting from here. The air flowing from the layer of the liquid attached to the surface of the interiors. They will carry out a certain amount of liquid droplet. Finally, when they impinge out, liquid will follow the surface of the injectors. Then when they impinge out, they will produce the surface, the spray cone. And you can see here, this wavelength occurs, okay, and break up to the ligament. Because we take a cross section, you need to figure out this cross section of a donut shape, and this is a ligament. And this ligament further be break up to the droplets. Okay, similar way to be found from the different kinds of mixing coming from different kinds of atomizing injectors, but they give you the same idea. There is the wavelength occurs, wave disturbance occurs on a shift to break the shift to the ligament, and the wave disturbance on the ligament will further break up the ligament into the droplet. This is a sequence of the the breakup mechanism. But for the atomization in real application used for combustion, people try to reduce the atomization mechanism as small as possible. That means we try to prevent those kinds of liquid sheets or ligament, because for the liquid sheet or for ligament, actually the liquid volume is still large enough and require more time to finish the gasification. People try to consider to have a possibility, for example, just like a simplex atomizer. This is the case. We are working on it. We try to suppress or try to reduce the region for sheet and ligaments to the minima, almost not detectable. Therefore, you will have a droplet occurs starting from the vicinity of the injector, the exit plane of the injector. And this is a good one for our application because you just have a liquid, many tiny droplet liquid exist in your combustion chamber. Then you can easily promote the gasification and further the mixing of the fuel vapor with oxygen from the air, then go through the combustion. Okay. Okay, now we will go to some theoretical descriptions on the spread characteristics later.